Let us discuss about another type of group, that is group of transformations. A transformation is a rotation or a reflection or a permutation, etc. is called transformations. Transformations which leaves the system invariant is called a symmetry transformation of the system. Example for symmetric transformations are rotation of a circle, permutation of two identical elements in a molecule. Okay, a set of symmetric transformation of a system forms a group. So, set of symmetric transformation of a system. This system may be a cube, a triangle, or a cube, or any polygon have a regular shape. So, the condition for these transformations form a group is the composition of any two symmetric transformation of system is a symmetric transformation. We know if we do two symmetric transformations, we will get another symmetric transformation. So, the system is closed. Here it is transformation of the system, not if. Okay. Every symmetric transformation do have an identity transformation, or it can be called as an identity element. We can define an identity element or identity transformation which leaves the system unchanged. Also, there should exist an inverse transformation in this group. And the successive transformation of the system also obey the. Now let us examine the group of symmetries of a square. So this is a square. Its sides are A, B, C, D are corners, and F, G, H, E, F, G, H are centers of edge. Okay, what is a dihedral group? So this is not E, it's I. Dihedral group. A group of symmetric transformation of a regular polygon which include rotation, reflection, etc. forms a group. So that group is called a dihedral group. So dihedral group is a symmetric symmetric transformation group of a regular polygon. Regular polygon may be a triangle or a cube or a square, anything like that. So here we are discussing the group elements of a square. So a regular polygon with n side have 2n different symmetric operations. Here n, it have n rotation operation and n reflection operation that we will discuss later. Okay, usually we take a polygon with a side n is greater than or equal to 3. So we start with a triangle, then a square, then like that. So, in order to study the symmetric operation of the square, okay, let us cut the square from a paper. Okay, so this 1, 2, 3, 4, 5, 6, 7, 8 points are marked in the paper, and from that paper suppose we cut the square. It is internally it is marked as A, B, C, D, E, F, G, H. So all symmetric transformations are the transformation which leaves the position of the boundary of the square unchanged. So after a transformation, suppose after a rotation, is that if we fit the square into that paper, it should match with its original shape. Then that type of rotation, we can call that type of rotation as a symmetric transformation. So അതായത് നമ്മൾ ഈ സ്ക്വയറിനെ റൊട്ടേറ്റ് ചെയ്യുന്ന സമയത്ത് ഈ സ്ക്വയറിന്റെ ബൗണ്ടറീസ് ഇതേപോലെ റെക്ടാംഗിൾ ഷേപ്പിൽ തന്നെ നിൽക്കണം. പക്ഷെ ഇത് വേണമെങ്കിൽ 90 ഡിഗ്രി റൊട്ടേറ്റ് ചെയ്താൽ എ ഈ പൊസിഷനിൽ എത്താം, ബി ഇവിടെ എത്താം, സി ഇവിടെ എത്തും, തിരിച്ച് ഡി ഇവിടേക്ക് എത്തും. സോ അതൊരു സിമെട്രിക് ട്രാൻസ്ഫോർമേഷൻ ആണ്. ഓക്കെ, പിന്നെ 180 റൊട്ടേറ്റ് ചെയ്ത് കഴിഞ്ഞാലും ഇതേ ഷേപ്പ്, ബൗണ്ടറി ചേഞ്ച് ചെയ്യുന്നതിൽ ഇതേ ഷേപ്പ് കിട്ടും. സോ ദാറ്റ് ഈസ് ഓൾസോ എ സിമെട്രിക് ട്രാൻസ്ഫോർമേഷൻ. അത്തരം റൊട്ടേഷനെ നമ്മൾ വിളിക്കുന്ന പേരാണ് സിമെട്രിക് ട്രാൻസ്ഫോർമേഷൻസ്. അപ്പോൾ ആ സിമെട്രിക് ട്രാൻസ്ഫോർമേഷൻ കണ്ടിന്യൂ ചെയ്ത് കഴിഞ്ഞാൽ നമുക്ക് ഈ ഒറിജിനൽ സ്ക്വയറിനെ വീണ്ടും കിട്ടും. പൊസിഷൻസ് എ ബി സി ഡി അതുപോലെ തന്നെ കിട്ടും. സോ ഓരോ ട്രാൻസ്ഫോർമേഷനും സിമെട്രിക് ആണ്. എ ഇവിടെ എത്തും, ബി ഇവിടെ എത്തും, പക്ഷെ ഈ ഷേപ്പിന് ഒരു ചേഞ്ചും സംഭവിക്കുന്നില്ല. സോ അത്തരം ട്രാൻസ്ഫോർമേഷനെ നമ്മൾ വിളിക്കുന്ന പേരാണ് സിമെട്രിക് ട്രാൻസ്ഫോർമേഷൻസ്. ഒരു പോളിഗണിനെ സംബന്ധിച്ചിടത്തോളം അതിന്റെ ഒരു സിമെട്രിക് ട്രാൻസ്ഫോർമേഷൻ 2π/n എന്ന് പറയുന്നത്. ഇഫ് n is the number of sides. ഇപ്പോൾ നമ്പർ ഓഫ് സൈഡ്സ് ആണെങ്കിൽ അതിന്റെ 2π/n റൊട്ടേഷൻ എന്തായിരിക്കും? ഒരു സിമെട്രിക് ട്രാൻസ്ഫോർമേഷൻ ആയിരിക്കും. ഇൻ ദ കേസ് ഓഫ് എ സ്ക്വയറിന്റെ കേസിൽ എത്ര സൈഡ്സ് ഉണ്ട്? 1 2 3 4 സൈഡ്സ്. അപ്പോൾ 2π/n എന്ന് പറയുന്നത് 2π/4, ദാറ്റ് ഈസ് π/2. നമ്മൾ അറിയാതെ തന്നെ പറഞ്ഞു π/2 റൊട്ടേഷൻ. ഇവിടെ നിന്ന് ഇങ്ങോട്ട് എത്തുക എന്ന് പറഞ്ഞാൽ അതൊരു π/2 റൊട്ടേഷൻ ആണ്. അപ്പൊ അതൊരു സിമെട്രിക് ട്രാൻസ്ഫോർമേഷൻ ആണ്. ഓക്കെ, സോ ഇനി ഏത് പോളിഗണിനെയും നമ്മൾ 2π/n, വേർ n ഈസ് ദ സൈഡ് ഓഫ് ദ നമ്പർ ഓഫ് സൈഡ്സ് ഓഫ് ദ പോളിഗൺ എത്ര സൈഡ്സ് ഉണ്ടെങ്കിൽ ആ സൈഡിൽ റൊട്ടേറ്റ് ചെയ്ത് കഴിഞ്ഞാൽ 2π/n റൊട്ടേഷൻ കൊടുത്താൽ that is a symmetric transformation. So if we rotate the polygon through a 2π/n degree about some axis, leaves the system invariant, then the axis is known as n-fold symmetric axis of the system, and corresponding operation can be represented by this Cn. Again, the integral power of Cn is also a symmetric transformation, that is Cn. So in the case of a rectangle, what is n? They have 4 sides. This is C4. What is C41? C41 indicate a rotation through 90 degree. Then what is C42? C42 is a rotation to 90 plus 90, 180 degree. That is again a symmetric transformation. So again Cn3, that is rotation through Cn means C43. In the case of a square, it is C43. That is equal to 270 rotation. So this C43 can be written as C4 minus 1. What is C4 minus 1? It is rotation through 90 degree in the counterclockwise direction. So this C43 and C4 inverse both are same. Then we again do a rotation, that is C44, that is equal to 360 rotation, or we can call this as an identity transformation. അപ്പോൾ എന്താ ചെയ്യുന്നത്? When we rotate this through C41, C42, C43 and C44, so this is a closure property. Groups it's obey the first property known as the closure property. Along with the rotation, a square have another 4 symmetric operation, 4 symmetric operation, that are 4 reflections that also make the square unchanged. So they are reflection through x-axis, that is we can reflect the square along the x-axis that make the square unchanged, or reflection about the y-axis, this reflection make the square unchanged, and another reflection is reflection through this diagonal elements, and this AB is one diagonal, BD is another diagonal. So this 4 reflection along with the 4 rotation do this a square have for reflection group also. So all these are the elements of the symmetric transformation group of a square. These are the elements E, C1 dash, E, C41, C42, C43, Mx, My. This is represented by sigma U, and this is represented by sigma V, that we can find in our next slide. Okay. So let us examine the identity element. It is A, B, C, D. So when we do a rotation of 90 degree in the clockwise direction, it will be like this. So A is shifted to here, A, B, C, D, 90 degree rotation. So you can cut a paper and can do this operation. Okay, so you will get a better idea about this symmetric operation. So when we do again C42 operation, what happened? It A, B, C, D rotate through 180, that is here 90, so it will here 180. So this is the C42, the C42 element. Okay, so when we do the C43, the square will be like this, and we do the reflection along x-axis. So this is the x-axis. When it is reflected, AB become here and DC become here. So this is DCAB. So reflection along y-axis, when we reflect, it is in the y direction. So you will get DC here, AD here. So when we reflect along this, you will get AC unchanged, and this will change, B and D interchanged. So this is usually represented by sigma U, and this is sigma V, that is reflection in the line 2, 4. So this B, D unchanged, and C and A interchanged. So this is the group after this is the square after this reflection in the line 2, 4. So we can take to convention. That is, when I asked you to rotate a square, you usually rotate the square in clockwise direction, and you fixed your XY set unchanged. So that we did in our previous topic. So that type of rotation is known as the active point of view of rotation. So we can rotate the square in another way also. That is, to make the square fixed, and we can rotate the coordinate but not in the clockwise direction, but in the anti-clockwise direction. That type of convention is known as the passive viewpoint. So we have two type of transformation of coordinate, that is, we can do either in active point of view or in passive point of view. So here this is the passive point of view. So here this square fixer, and we rotate the axis in the counterclockwise direction in 90 degree. So this we will get all the elements of the group formed by the symmetric transformation of square. Now let us check whether the 8 transformations form a group or not. So we can do one type of operation, that is sigma U and C41. So normally when in this case, when we do this operation sigma U and C41, so first we have to do the C41, and then we has then on that sigma V is acting. That is, always the operation take place from right to left, not from left to right. So this should be in your mind. All the operation, you have to operate all the operation from right to left. Okay, so when we do the operation, so if cu c41, if c41, c42, c43 and identity element, then mx, my, sigma u, sigma v form a group, it have to obey the closure properties. So when we multiply any these two elements, it should be in the group of in the group of this in the group. So that is then only the closure property will satisfy. So let us check whether sigma u c41 dash is obeying the closure property or not. So when we check for that, sigma u c41 a b c reacting on it. So first the c41 should operate on a b c d. So this will become a become here b, so it rotate by 90 degrees. So a b c d like this, it will transform like this. Then sigma u is acting on this. Sigma u is a diagonal operation, so db unchanged, so we can change c and a. So this is db, c and a. This is nothing but this mx is acting on a b c d. We just look at what happened to mx acting. ms acting on a b c d means here this x is in this direction, then a b and dc are interchanged. You will get dc here, ab here. So this is a kind sigma u c4 dash. So sigma u c4 dash can be written as c41 is can be written as mx. So this obey the operations obey the closure property. So like above, you have to do all the operations. So we write the multiplication table. Don't write blankly. You have to do each operation. So this is, we can write writing this element on the on a group multiplication table. The order is not important. We can write e c4 c42. You can write in any order. You can write c4 here, here. Okay, no such restriction is for writing the multiplication table. But in this multiplication table, I write e c4 square, c4 cube, mx, my, sigma u, sigma v, and here I write e c43. c43 is inverse of c4. You can check it. Okay, now you know how to do this operation. So just check it. What is c4 and c43? Then you will understand that the inverse of c4 is c43. Well, we know that c43 is c4 inverse, that we proved our second slide or like that. Okay, so this is c43 and c4 inverse of c42 is c42 again. Then c43 inverse is c4 and mx is the inverse of mx, my is inverse of itself, and sigma u is inverse of itself, and sigma v is again inverse of itself. So that you can check. You check it by doing these operations. Okay, it is a compulsory thing. Don't write the things blankly. You just do all the operation, then find out all the operation and find out all the elements of the multiplication table. Okay, so why I like this write like this is that if we write like this, when we write the element here in this order and we write the inverse of this in this order, then you will get the diagonal element as e. You can write this in any order, there is no problem. So e will be somewhere like maybe in any other positions. So in order to get the diagonal e element, if you write in this order, you will get e as a diagonal element of this square matrix. So you can take any convention and you can take any order. There is no problem for that. So you have to do all the operations and find out what is the product. So when we do this operation c4, first you have to do the c4 operation, then you have to do the c43. So we can write this is c43 c43. We can you will get this element by doing the operations, c43 c4. So first you operate c4 on the ABCD, then you have to do C for 3 on that. So you will get the element, identity element E. So likely you can do all the operations. Okay. So let us examine what is generators of finite group. It is possible to generate all the element of the group by starting from certain set of element which are subjected to some relationship or operation. These elements are called generators. If a single element generates all the group elements, then that element is called a generator of that group. That we are seeing in the case of a cyclic group that we discussed in our earlier classes. Okay, so if G is equal to A, all the elements can be represented. The element of G, if the element of the G can be represented like this, that is A square, A cube, A raised to N, that is equal to E. So here A is a generator of the group. So suppose here A raised to N is E. Suppose what is suppose what is A raised to N plus K. A raised to N plus K can be written as A raised to N into A raised to K. That is, what is A raised to N? A raised to N is identity element, so A raised to K. So this A raised to N plus K is not a new element. It is again in this group. So it obey all the properties of the group.